In this unit, we are going to talk about metabolism, which involves the production of energy for our cells' use, as well as how our cells are going to use that energy. The first part of this unit does involve the various cycles or pathways in the body that are in our cells rather, that are used to make energy. This can become very confusing. One advantage to having the videos like this is you can listen to it many times. If you don't get it the first time through, listen again and even listen again. If there is something you still are having issues with, please let me know, and I will try to work with you and make sure you understand. So, starting with an introduction to metabolism. Our cells break down organic molecules in order to obtain energy. They use these organic molecules to make ATP. We talked about ATP last semester and referred to it as the energy currency of the cell. Currency, like money. The more ATP a cell has, the more things they are going to be able to do. This process of making ATP is known as oxidative phosphorylation because in order to do this, the cell needs a steady source of oxygen. So this chapter brings together the two previous chapters we have talked about. We've looked at how our body gets oxygen, and we've also looked at how our body gets these organic nutrients. Now we're going to look at how the body uses oxygen and these organic nutrients to produce energy. Most energy production takes place in the mitochondria. Remember last semester when we did the cell, we nicknamed the mitochondria the powerhouse of the cell because this is where the power, the energy is coming from. A definition of metabolism. This term refers to all chemical reactions that occur in an organism. We are going to focus at the cellular level, and this is known as cellular metabolism, all chemical reactions that occur within a cell. Cellular metabolism is what provides energy for our cells in order to maintain homeostasis and to perform essential functions. And you can see some of these on this picture. They need ATP, energy, for maintenance and repair of the cell, in order for the cell to grow, in order for the cell to, for example, if it's a muscle cell, to contract, intracellular transport, etc., etc. Metabolism involves two basic processes. The first is catabolism. Catabolism refers to the breakdown of organic substrates. Catabolism, when we break something down, this ends up releasing energy in the form of ATP. We can then use the energy that is produced through catabolism for the cell to be able to synthesize new components that they might need. So an example of catabolism would be when a cell takes a protein, which is a large organic molecule, and breaks it down into its individual amino acids. In doing so, it will release ATP. Catabolism is also what happens here in the mitochondria when they take simpler materials such as glucose and break it down into carbon dioxide and water. And again, in the process, release ATP. The second process is anabolism. Anabolism is the synthesis of new organic molecules by binding together smaller ones. Anabolism requires and will use the energy that was produced or released as a result of catabolism. So here we can see our cell can take materials from our pool, nutrient pool, amino acids, for example, take those amino acids and some ATP and build a protein that it might need. Many times, the materials, the raw materials that a cell gets may not be in the exact form that they need. So they will take that protein that they received, break it down into the individual amino acids, and then take those amino acids with some ATP and build the protein they do need. So this is the two major processes here, anabolism and catabolism. Let's look at this nutrient pool. And this is what our cell has to draw on, the nutrients our cell has to draw on for cellular metabolism. The nutrient pool contains all of the organic building blocks a cell is going to need, and it can either use those to make ATP, or it can use them to create new cellular components. So this nutrient pool acts as a source of substrates for both catabolism and anabolism. We can see it can go in both directions. Now, what nutrients are found in this pool? Vitamins, minerals, and our basic organic compounds, lipids, amino acids, sugars, etc. The function of these organic compounds is, one, to perform basic structural maintenance and repair using these proteins that the cell makes to repair anything that the cell might need. They can be used to support growth of the cell and cell division. They can be used to produce the secretions that a cell is going to make, and to store nutrient reserves within the cell. What are some of these larger organic compounds? One main one is glycogen. Glycogen is how our cells, as well as our body, stores carbohydrates. And we'll see later on in this unit, the liver, for one, is vital in storing excess glucose in the form of glycogen. Glycogen is made up of strictly glucose. Triglycerides is how our body and our cells store lipids. A triglyceride is made up of 3 fatty acids, hence tri-3, and 1 molecule of glycerol. And then lastly, proteins. Proteins are the most abundant organic component in the body. Most of our body, the main organic material is protein. Proteins perform many vital cellular functions. And remember, the building blocks of proteins are amino acids. All right, we're going to focus on carbohydrate metabolism, how our cells use carbohydrates. Carbohydrates are the first organic material that our cells are going to go for in order to produce ATP. In many instances, carbohydrates are the easiest compound for our cells to break down and get ATP from it. Before we look at this, we need to take a closer look at our mitochondria, because we said the bulk of metabolism, cellular metabolism, occurs here in the mitochondria. Remember from last semester, our mitochondria is described as a double membrane organelle. The outer membrane here contains large diameter pores that are permeable to ions and small organic molecules. This makes sense. Remember, we said that most of cellular metabolism takes place inside the mitochondria. So we have to be able to get these materials inside the mitochondria, and they will pass through these pores. The inner membrane contains a series of carrier proteins. These are the blue molecules that you see represented in this picture. These proteins, or these carrier proteins, move molecules into the center portion of our mitochondria, which is known as the matrix. And then between these two membranes, we have what's called the intermembrane space. This just separates the outer and the inner membrane, and we're going to see that it plays a key role in one of the steps of our cycles. So the purpose of carbohydrate metabolism obviously is to generate ATP, but it can also generate other high-energy compounds through the process of breaking down carbohydrates. Remember, all carbohydrates are made up of sugars, and when you take a sugar in the presence of oxygen, it will be completely broken down into carbon dioxide and water. There are 2 basic steps involved in carbohydrate metabolism: glycolysis and cellular respiration. We're going to start with the process of glycolysis. This is the only cycle that occurs outside of the mitochondria. That's important. Glycolysis does not use the mitochondria. It occurs in the cytoplasm outside of the mitochondria. Glycolysis is a 10-step process whose function is to break down one 6-carbon glucose molecule into 2 3-carbon pyruvic acid molecules. And then it's the pyruvic acid molecules that will go on to the mitochondria for the remaining processes. So again, here we have 1 6-carbon glucose, goes through all of the steps and end up as 2 molecules of pyruvic acid. Each molecule of pyruvic acid has 3 carbons. We have maintained the total number of carbons. This is very important. Now, I also said that this is a 10-step cycle. Well, then why do we only see 7 steps here? Your book has combined a couple of steps just to simplify the process. You are not responsible for the individual steps. I will go through specifically what I want you to get out of this. First, what is the starting material for glycolysis? That is glucose. And again, very important, glucose is a 6-carbon molecule. What is the end product? In other words, what does glycolysis produce from that glucose? The end product are 2 molecules of pyruvic acid. Each has 3 carbons in it. So from 1 glucose, we're going to get 2 pyruvic acids, each of which will continue with the rest of the cycles. That's important to remember. Each pyruvic acid is going to continue. 1 glucose gives us 2 pyruvic acids. The other thing that's important with this cycle, we said the whole purpose of carbohydrate metabolism is to produce ATP. So how many ATPs are we getting? Let's look at the beginning. Look at step 1 and 2. I thought glycolysis was supposed to make ATP, but look what's going on here. The cell is using ATP. Right in the very beginning, our cell has to spend vital ATP to get the process going. This is known as an investment. Just like with money, you have to invest money to make money. Our cell has to invest ATP to make ATP. So here, this bullet point, how much ATP does our cell need to use, need to invest to get the process started? The answer is 2. We need to invest 2 ATPs. Now, follow the steps down. Okay, so we're in the hole here. We're at a minus 2 ATPs. All right, so come down to this one. In this step, we made 2 ATPs. All right, now we've broken even. We used 2, we made 2, we broke even. We come down a little farther, we make another 2 ATPs. All right, there are 2 ways I can ask, or 2 things I can ask about this ATP. First, how many total ATP did our cell make in glycolysis? How many total ATP did the cell make? It made 2 here and 2 here for a total of 4 ATP. The other question I can ask is how much usable ATP did our cell get? In other words, what is the net gain? Okay? Net gain, if you had to invest $2, but you made $4 on that investment, how much did you really make? You made $2. That's the same with our cell. We invested 2 ATPs and got 4 ATPs from that investment. So we had a net gain of 2 ATPs, 2 ATPs that our cell can use elsewhere. Okay. So again, how many ATPs did we have to invest? 2. How many total ATPs were made in glycolysis? 4. What is our net gain of ATP, usable ATP? 2. Now, there's something else I want you to keep track of as we go through, and that is this material here that's in the orange. This is known as NADH. This is going to be very critical at a later cycle. So how many NADHs do we make in glycolysis? We make 2. Okay? So all of this is highlighted here. We invest 2 ATP, we make a total of 4 ATP and 2 NADHs. Our net gain of ATP for one glucose molecule is 2. So if we look at how many total ATP do we have right now, when glycolysis is done, we have a total of 2 usable ATPs for our cells. And as I said before, our end product are these 2 pyruvic acids. They are going to continue with the rest of the cycles. Now, unfortunately, this little video doesn't work. It's not supported anymore by the newer versions of PowerPoint. But if you still have questions, there are very good videos that you can Google on YouTube as well that will help to illustrate this process. But again, if you're still having issues trying to figure out where things are coming from, please let me know. All right. Now, those 2 pyruvic acids are going to continue on to our next cycle, which is known as the citric acid cycle. It's also known as the TCA. It's known as the Krebs cycle. It goes by a number of different names. This picture is only going to follow one of those pyruvic acids. Remember that there are 2 pyruvic acids made from each glucose. The TCA cycle occurs in the mitochondria. Okay, so now that pyruvic acid that was just made is going to be shuttled into the mitochondria to continue these processes. Now, before our pyruvic acid can enter into this cycle, it has to be prepared. So this is like an extra step before the TCA. So we have to convert the pyruvic acid into acetyl coenzyme A that will then enter into this cyclic here cycle. Notice, as we prepare pyruvic acid, we get an NADH. We got to keep track of these. I don't have this NADH accounted for on the slide, but this is going to come up in a later calculation. So just remember, this is a preparatory step. Okay, we're preparing that pyruvic acid to enter into the cycle. So in the preparation of that material, we produce an NADH. Here's a question. From our glucose that we started with, how many NADHs are we going to get from this prep stage? 1 pyruvic acid will give 1 NADH. But remember, we have 2 pyruvic acids coming from that glucose. So that second one will also give an NADH. So in this prep stage, we will get a total of 2 NADHs from that original molecule of glucose. I know this can be confusing. Go back and look. Follow the numbers. All right. Now, the TCA cycle itself. As I said, 1 pyruvic acid is going to be prepped to go into the cycle. And I can't emphasize enough, we have 2 pyruvic acids from that original glucose molecule. So once this pyruvic acid is prepped, it will go around the circle. Now look what we get as we go around the circle. 1 turn of the circle produces 1 ATP. It also produces 1, 2, 3 NADHs. And it produces another material similar to NADH that we also need to follow. This is known as FADH. 1 pyruvic acid gives us 1 turn of the circle to give us 1 ATP, 3 NADHs, and 1 FADH. But remember, we have 2 pyruvic acids coming through from that original glucose. So we get a second turn of the cycle to give us a second ATP, 3 more NADHs, and 1 more FADH. So if we're keeping track of the ATPs, how many ATPs do we get from one glucose when it makes its way to the TCA cycle? We get a total of 2. 1 from each of the pyruvic acids made from that glucose. How many total NADHs are we going to get from that original glucose? We will get 6. 3 from each of the pyruvic acids. And how many FADHs will we get from that original glucose? We will get 2. 1 from each of those pyruvic acids. All right, so now in red here, this is keeping track of the ATPs. So far, we have made a total of 4 ATPs. That doesn't sound like a whole lot, and really, it isn't. We'll see where the rest of these ATPs are coming from. Now, something else I want to point out here. If oxygen supplies are adequate, the mitochondria will absorb and break down the pyruvic acid molecules. This step only occurs, and carbohydrate metabolism only proceeds to the mitochondria if oxygen is present, if there is enough oxygen to support it. Remember on the first slide, we called this oxidative phosphorylation. Now look what happens. We have oxygen. We're going to break down this molecule. The hydrogen atoms from that pyruvic acid are going to be removed by coenzymes. That is the NADH and the FADH. They're NAD, they pick up that hydrogen, or FAD, picking up the hydrogen. NAD and FAD are known as coenzymes. And we're going to see that these NADHs and FADH are going to be the primary source of all energy gain. They are going to be the materials responsible for the large productions of ATP. Carbon and oxygen atoms are also going to be removed, and as the pyruvic acid goes through, and as carbon is removed, carbon and oxygen, okay, this is where the CO2 comes from. And carbon dioxide, remember, is a byproduct of respiration. It's a byproduct of cellular respiration. As we saw in the respiratory chapter, as the CO2 accumulates in the cell, it will diffuse out into the blood to be taken back to the lungs so we can exhale it. When glycolysis and the TCA cycle are complete, as we saw, we have a total of 4 ATPs. Now, we get a lot more ATP from these processes. Where does the rest come from? Right? It's going to come from these, the FADH and the NADHs. Now, let's make sure you understand we're saying 2 FADHs and 10 NADHs. Where are these coming from? The 2 FADHs, okay, came from here. Each pyruvic acid produced 1. We get 2 pyruvic acids from 1 glucose, hence 2. Now, what about the 10 NADHs? All right, let's go back to this one again. From 1 pyruvic, we're going to get 1 NADH as it's prepped, and 3 from the cycle. So that's 4. And remember, we get 2 pyruvic acids from that glucose, so we double that number to 8. But we say 10. Where'd the other 2 come from? Go back, jumping back, go back to glycolysis. Right there's our other 2. Right, so we have 2 NADHs from glycolysis and a total of 4. And another 4, 8, plus 2, here's our 10. Okay, keep going through that. Make sure you understand where these are coming from. All right, so these FADHs and the 10 NADHs are going to go on to our next step, which is the electron transport system. And in the ETS, these FADHs and NADHs will be used to make another 32 ATPs. All right, so now we're going to look at the electron transport system. This occurs in the inner mitochondrial membrane. It uses those series of carrier proteins that we identified in the inner mitochondrial membrane. Electron transport. So this is going to involve the transport of electrons. Electrons are what actually transfer the energy. And these electrons will travel through a series of oxidation-reduction reactions. Oxidation is the loss of electrons, and reduction is the gain of electrons. These electrons ultimately combine with oxygen at the end of the cycle to form water. Now, when we talk about electrons carry a negative charge, so electrons are actually carried with hydrogen ions. Hydrogens carry a positive charge. So instead of following the electrons, we actually look at and follow the hydrogens. So let's look at the oxidation and reduction in a little bit more detail. Oxidation is defined as the loss of electrons. An electron donor is a molecule that, if a molecule donates or gives up or loses an electron, it is said to be oxidized. Hence, the process is known as oxidation. Reduction is the gain of electrons. Whoever is going to receive or pick up or gain these electrons is said to be reduced. And these two reactions are always paired in a cell. So as one molecule is losing electrons or losing hydrogens, another compound is right there to gain those electrons and gain those hydrogens. All right, what happens in the electron transport system? Here's our mitochondria. Here's our outer membrane. Here's our inner membrane with those transport proteins, and here's that space between. So the electron transport system is a sequence of proteins, involves these proteins that are embedded in that inner membrane of the mitochondria. The goal of these proteins is to remove the electrons, i.e. the hydrogens, from the FADH and NADHs that were produced in the previous steps. These carriers will then use those electrons to pump hydrogens from one side of this membrane to the other. They pump these hydrogens into that space between the two membranes. Each NADH that comes in can fuel the electron transport system to pump a total of 6 hydrogens into that space. So here's where NADH comes in, and 2, 4, 6 hydrogens will be pumped across that membrane as a result of one NADH. FADH enters a little bit later. So when FADH comes in, it can only result in pumping 4 hydrogens across. But either way, 6 for every one of those NADHs, 4 from every one of those FADHs that were produced. Think about all of the hydrogens that are being pumped into this space. In the end, this produces a concentration gradient. All of these, a very high concentration of hydrogens trapped in the space. These hydrogens want to get back inside. They're out here all by themselves, and they're bouncing around. They're all hyped up, trying to figure out, how am I going to get back inside? Think of them as just little kids hyped up on sugar, bouncing all around, trying to figure out, and they all want to get back in where they belong. Right? This is what's happening. At the very end of this chain, you will find an enzyme. This enzyme is known as ATP synthase. So what this enzyme says, okay guys, you want to come back inside? This is your only way back. I will let you come back inside, but as you come through my channel, I'm going to strip you of all your energy. So all these hyperhydrogens pass through, and when they enter back in, they're nice and calm because this enzyme took all of their energy and used it to make ATP. This process is known as chemiosmosis. Remember, osmosis, right? We talked about being the movement of water. Chemiosmosis is the movement of a chemical, i.e. hydrogen ions. For every 2 hydrogen ions that pass through this enzyme, you will make 1 ATP. Repeat that. For every 2 hydrogens that go through that enzyme, you get 1 ATP. Go back to our NADHs. 1 NADH pumped 6 hydrogens into the space. How many ATPs can we make from those 6 hydrogens? 6 divided by 2 is 3. So for every 1 NADH that comes in, we will make 3 ATPs from it. FAD can only pump 4. 4 divided by 2 is 2. So every FAD that comes in will produce 2 ATPs. We're going to end up, as a result of the electron transport, a total of 32 ATPs. Where did these all come from? We said that there were 2 FADs coming in. 2 times 2, there's 4 right there. And we had a total of 10 NADHs from that glucose that were made. 10 times 3 is 30. 30 plus 4, that's 34. But I say here, there's only a net gain of 32. Hold that thought. I'll explain why. Yes, the potential is there to make 34 ATPs, but we only get 32, and I will explain why the discrepancy. So now, if we take this 32 ATP with the 4 we made earlier, 2 from glucose, 2 from the TCA, 32 plus 4 gives us a total of 36 ATPs from 1 molecule of glucose. So again, this video unfortunately is not supported anymore. Make sure this is probably the most important diagram summarizing carbohydrate metabolism, showing where and how we get these 36 ATP. We already said we have a net gain of 2 ATP from glycolysis. We see that up here. We made 4, but we had to use 2, so we have a net gain of 2. We got a total of 4 NADHs. Here, we're going to get 4 ATPs from the NADHs that were made in glycolysis. This is where the discrepancy comes in. We said we made 2 NADHs from glycolysis. Those 2 NADHs should produce 6 ATPs when it gets to the ETS. We only get 4 from them. Why? Because these NADHs are made in the cytoplasm, and we have to get them into the mitochondria where the electron transport system is. They lose some of their energy potential in that transfer across the membrane. So instead of getting a total of 6 from them, we are only going to get 4, and that's highlighted right here. 4 ATPs from those NADHs made in glycolysis. We get 2 ATPs made directly here from the TCA cycle, and then the remainder 28 from all of these NADHs made from TCA and the FADHs made from TCA gives us the other 28. Add these all up, and here is where you get your total of 36 ATPs. Again, keep going over this. Make sure you understand where all of these are coming from. All right, some other aspects of carbohydrate metabolism. Gluconeogenesis. Break this word down. Genesis means creation, neo means new, and glucose. It is this creation of new glucose. Gluconeogenesis is the synthesis of glucose from non-carbohydrate precursors. We're making new glucose from something that is not a carbohydrate. We're taking lactic acid and turning it into glucose, glycerol and amino acids and turning them into glucose. Glycogenesis, creation of glycogen. This is the formation of glycogen from glucose. Again, this is how our body stores glucose in the form of glycogen. And then glycogenolysis, lysis of glycogen. This is the breakdown of glycogen to create or produce glucose. Now, another nutrient molecule our body can use for energy are lipids. So we're going to briefly look at lipid catabolism, also known as lipolysis. Lipid catabolism will break lipids down into smaller pieces that can either be converted into pyruvic acid or can go directly into the TCA. So this does not start at the beginning of glycolysis. The breakdown products of lipid catabolism will either be directly converted into pyruvic acid and start there, or they are converted into components of the TCA cycle and enter into the process at that point. Each triglyceride molecule is one molecule of glycerol and 3 fatty acids. That one molecule of glycerol can be converted into pyruvic acid, or it can be channeled directly into the TCA cycle. Glycerol is a 3-carbon molecule, so it's very easy to directly convert it into pyruvic acid. The 3 fatty acid molecules, they will go into the TCA cycle, but first they have to be broken down into 2 carbons at a time. So remember, fatty acids are long chains of carbons. These fatty acids will be broken down, 2 carbons at a time will be broken off of that molecule and shunted into the TCA cycle. For each 2-carbon fragment that was removed from that fatty acid, look at how much ATP our cell can gain. We can get 12 ATPs from the TCA, 1 ATP directly, and 9 from the 3 NADHs, and 2 from that 1 FADH. We will also get 5 ATPs from the NADH and FADH that's generated in just removing and prepping that 2-carbon fragment. So a cell can gain a total of 144 ATP molecules from 1 8-carbon fatty acid. That is a huge amount of energy gain from 1 fatty acid. And please, I will never ask you to calculate or figure out or trace where these ATPs come from in a lipid. It's more important in the carbohydrates, but this gets way too complicated to try to figure out where they are all coming from. But just know that you can get a lot more ATP. So fatty acid breakdown yields about 1.5 times the energy of breaking down a molecule of glucose. You may say again, but we only got 36 and here we're getting 144. That's almost 3 times. Well, there's a lot of prep work that goes into breaking down this fat. And this is also why our body is so reluctant to use our stored lipids for energy. Carbohydrates are easy to break down, very easy to process. Lipids, they're not water soluble, remember, and they need a lot more special handling in order for our body to be able to get even to this point. So there is a much bigger energy investment when we break down a lipid. So hence, yeah, we get 144. It looks like a huge energy gain compared to glycolysis, but we actually had to use a lot of that ATP just to prep this fat. So again, our body would prefer to use carbohydrates because it's easier. And that's why we store fats and why it is so hard when you are losing weight to try and burn and you get your body to use these stored fats for energy. Lipid synthesis is known as lipogenesis. Again, creation, genesis, lipo of lipids. Lipid storage is important to our bodies as an energy reserve because, as we just saw, lipids can provide large amounts of ATP, but it is a very slow process. Also, the reason our body tends to store carbohydrates in the form of lipids is because it saves space. But it's very hard for our water-soluble enzymes to reach these lipids to begin to break them down. So our body will store excess carbohydrates in the form of lipids because it saves space. It takes less space to store them as a lipid than it does to store it as glycogen. But once we make that lipid, it's very hard to break it down because our enzymes can't get there. They can't reach it because most of the enzymes involved in these processes are water soluble. Lipid transport. Our cells require lipids. Lipids are critical to our cells. Lipids are needed to maintain the cell membrane. They're one of the major components in our cell membrane. Circulating lipids, I've said all along that they are not water soluble. Most lipids circulate through the bloodstream in the form of a lipoprotein. Free fatty acids are a very small percentage of the total circulating free lipids. Now, our other major nutrient are proteins. Our body synthesizes roughly 100,000 to 140,000 different proteins. Each one of these proteins has a different structure, form, and function in our cells. All proteins, remember, are built from only 20 amino acids, 20 building blocks, that's all, to create all those different proteins that we need. Cellular proteins are recycled in the cytoplasm of the cell. So if the cell takes in a protein, it may not need that particular protein. It may need a different one. So the peptide bonds of that protein will be broken down, and then the free amino acids that are generated will be used to synthesize new proteins that the cell does need. Now, what about proteins and ATP production? Proteins will not be used for energy until all glucose and lipid reserves have been used up. So if glucose and lipid reserves are inadequate, then our liver can break down various internal proteins into amino acids. The liver can also absorb additional amino acids from the blood. And then we will use these amino acids to break them down to get ATP. Now, to use amino acids, the carbon chains would be broken down in the liver, and then the products of this breakdown will be sent to the mitochondria to make ATP. But the problem when we break down amino acids to make energy, ammonia will be produced as a byproduct. Ammonia is toxic to our cells, so we have to have a way of getting rid of this. So ammonium ions accumulate when amino acids are broken down. As I said, this is highly toxic to our cells, even at very low concentrations. So the liver has a way around this. Liver cells have enzymes that will use these ammonium ions and make urea. And this is known as the urea cycle. So the urea cycle is the reaction sequence that converts this ammonia into urea. And then urea is a major component of urine. It will be removed from the body by the kidneys. Protein synthesis we've already talked about earlier last semester. Protein synthesis occurs in the ribosomes of our cells using those 20 different amino acid building blocks. Our body is able to synthesize about half of the amino acids, half of these building blocks that are needed to make all of our proteins. So our amino acids are broken down into two groups. Non-essential amino acids. These are the 10 amino acids that our body can make on demand. We don't have to get these amino acids from our diet. Our body has all of the necessary enzymes to be able to do it themselves. The other set are called essential amino acids. 8 of these are not made at all by the body. The body has no means of making these 8 amino acids. The other two are partially synthesized by the body. So our essential amino acids we must get from our diet. We cannot make them, so we have to make sure that the foods we are eating account for these essential amino acids. Now, we're going to shift gears a little bit and look at how our body uses ATP and how it uses these different nutrients. We're going to look at the absorptive and post-absorptive state. The absorptive state is the period following a meal when nutrient absorption is underway. Okay? We've just eaten and the food is being digested and the nutrients from that food are going to be absorbed. The post-absorptive state is the period when nutrient absorption is not underway. During this time, the body must rely on internal energy reserves for their energy demands. This is also the time when our liver cells will conserve glucose or break down lipids and amino acids to try and get the nutrients we need. So this brings us to the liver. The liver, we looked a little bit at it in the last unit. The liver is the focal point of metabolic regulation and control in the body. The liver contains a wide variety of different enzymes that are able to either break down or synthesize virtually any carbohydrate, lipid, or amino acid the body might need. Our hepatocytes, remember, also have an extensive blood supply. Remember the structure of the lobule in the liver. The hepatocyte's job is to monitor that blood and adjust the nutrient composition of it as it passes through those channels. The hepatocytes also contain significant energy reserves. They will remove excess glucose from the blood as it's passing through and store it as glycogen. Then we can call on these glycogen reserves when we need glucose. Adipose tissue is also important because this is where lipids are stored, mainly in the form of triglycerides. Remember, adipose, okay, it's located, this adipose is located in adipocytes. And where can we find adipocytes? Adipocytes are the main cells that make up areolar tissue. Remember, areolar tissue becomes adipose tissue as it stores more and more lipids. Our mesenteries are a great source of adipose tissue. Remember the greater omentum, and I said that was nicknamed the fatty apron. Our red and especially our yellow bone marrow is mainly 100% adipose tissue. The epicardium, there is a layer, our heart is encased in a layer of adipose for protection. Same with our eyes and kidney. There is a pocket of adipose tissue behind our eyes for support and protection, and same with our kidneys. Our skeletal muscles, remember from last semester, we talked about how our skeletal muscles have a very high reserve of glycogen. This is going to support muscle contraction. They can break down that stored glycogen for glucose to support contraction. Contractile proteins can also be broken down and used as an energy source. This is something you do not want to happen. You would be in a very severe state of lack of nutrients if you begin to break down your muscle proteins. But in a pinch, yes, your muscles can be broken down, the proteins can be broken down, and these amino acids used as an energy source. Now, what about our nervous tissue? Our neural tissue does not maintain any reserve of either carbohydrates, lipids, or protein. They have nothing to fall back on. As a result, they require a large, reliable source of glucose. They cannot metabolize any other material. They need glucose. Remember last semester, how I said glucose is brain food. And our brain, our nervous tissue needs glucose to function. Our central nervous system cannot function in a low glucose state. If your blood sugar starts to fall, you notice that you start to feel a little woozy, and if it drops too low, the individual will become unconscious. All right, so now how does our body get all of these nutrients and materials that it needs to maintain proper homeostasis, to maintain proper energy production? So we're going to look a little bit at nutrition. Homeostasis can be maintained only if the digestive tract absorbs enough fluids and nutrients. It needs these organic substrates, minerals, vitamins, etc. to meet all of our cellular demands. Nutrition involves the absorption of nutrients from the food we eat, and our body's requirement for each of these nutrients varies. All right, so let's look at some of these important materials. First, we need nitrogen, and where we get the bulk of our nitrogen from are proteins. Complete proteins will provide all the essential amino acids in sufficient quantities for our body to use. Complete proteins are found in beef, fish, poultry, eggs, and milk. Incomplete protein sources are deficient in one or more of the essential amino acids, and these are typically the proteins that are found in plants. So anybody who is either a vegetarian or a vegan needs to be aware of this when they're starting that program, because you have to make sure you are getting all of your complete proteins, because you vary up your plants, making sure you are getting every essential amino acid that your body needs to be able to make the required proteins. We also need numerous minerals. Minerals are inorganic ions that are released through the dissociation of electrolytes. Think salt. You put salt in water, it dissociates into sodium and chloride. These are minerals. Minerals, or these ions that are created, are essential in the body. Sodium, chloride, and potassium help to determine the osmotic concentration of our body fluids, and we'll look at their significance in one of our next chapters. Many minerals act as cofactors in different enzyme reactions, especially magnesium and copper. What a cofactor is, it works with the enzyme. If that cofactor is missing or absent, the enzyme will not be able to function. And many of these metal ions assist in oxygen transport as well as in the electron transport system. This is a list of the major minerals that our body needs. Just sodium, potassium, chloride, very important in maintaining osmotic balance. Calcium, essential for muscle contraction and our bones. Same with phosphorus. And then many of these are cofactors. Magnesium, copper act as cofactors, as does manganese, cobalt. So this is just showing some of the major minerals that our body needs. We also need many vitamins. Vitamin A is the structural component of the visual pigment retinol in our eyes. We get vitamin A from our leafy vegetables as well as our yellow and orange vegetables. Vitamin D, we did a lot with last semester. Vitamin D is converted into calcitriol, which helps to increase the rate of intestinal calcium and phosphorus absorption. Remember that vitamin D is made in the skin when our skin is exposed to UV radiation or to sunlight. Vitamin E helps to stabilize the intracellular membrane. So it helps to stabilize the cell, the shape and the structure of our cells. It is found in a wide range of foods, including meats, milks, and vegetables. Vitamin C is a coenzyme, and it also acts as an antioxidant. It is found in fruits, especially our citrus fruits. Vitamin B12 is another coenzyme that is used in nucleic acid metabolism, and this is found primarily in meat. Our other B vitamins are important in the TCA cycle, and they also are found in meat. Vitamin K is used to synthesize several proteins, especially 3 vital clotting factors that are used in the blood coagulation cascade. Vitamin K is produced primarily by our intestinal bacteria. I said in the last chapter that as long as you have healthy E. coli in your GI tract, you will produce all of the vitamin K that you need. Vitamin K can also be found in many vegetables. All right, when we talk about our food, we talk about, and we will look at the calorie content of our food. Calorie content representing how much energy you are going to get from that particular food. Well, there are a couple of ways of looking at calorie. Calorie with a lowercase c, this is the energy required to raise 1 gram of water 1 degree Celsius. That is not the calorie that we see represented on our food. When we look at the calories in our food, it is a calorie with a capital C. This is the energy to raise 1 kilogram of water 1 degree Celsius. This is actually a kilocalorie, and we represent it with a capital C. Energy content of food, lipids, and this is per gram. A gram of lipid, a food that is high in lipids, will release roughly 9.5 calories per gram of fat. Carbohydrates release about 4.2 calories per gram, and proteins about 4.3 calories per gram. Now, we're always concerned about our metabolic rate and our basal metabolic rate. Our metabolic rate refers to the sum of all anabolic and catabolic processes in our body. Metabolic rate changes according to our activity. And here's the basis of all weight gain, weight loss. You need to balance what goes in with what goes out. If your daily energy intake is greater than or exceeds your energy demands, your body is going to store that excess energy as triglycerides in your adipose tissue, and you will gain weight. If your daily caloric expenditures is greater than your dietary supply, in other words, you are expending more calories than you are putting in, your body is going to be forced to use your energy reserves, and this is when you lose weight. So one measurement is our basal metabolic rate. The basal metabolic rate is the minimum resting energy expenditure of an awake and alert person. And this will be measured when they determine it under standardized testing conditions. What they do to measure the BMR, it involves monitoring your respiratory activity. Why? Because energy utilization is proportional to oxygen consumption. Okay, so that we use oxygen to make that ATP. So by monitoring your respiratory activity, okay, it's going to give you an idea of your energy utilization. Think about it. When you're exercising, you're breathing heavier and deeper. You're bringing more oxygen in. You're consuming more oxygen to make that energy to support that exercise. So energy utilization is proportional to the amount of oxygen consumption. Now, various things can have an effect on your metabolic rate, especially hormones. Thyroxine, T4, controls overall metabolism. We looked at that in the endocrine chapter. Somebody who is hyperthyroid, has too much thyroid hormone, has a very high metabolic rate and burns calories at a very rapid rate. Cholecystokinin, CCK, as well as ACTH help to suppress the appetite. So you should not take in you're trying to prevent you from taking in as many calories. Leptin does the same thing. Leptin is released from adipose tissue during the absorptive state, when your body is absorbing nutrients. Leptin binds to the central nervous system neurons and helps to suppress your appetite. Your body right now is dealing with all these nutrients that you just ate. It doesn't need any more nutrients, so it suppresses your appetite, so you are not hungry. Thermoregulation is also important to look at with your metabolic rate. The body produces heat as a byproduct of metabolism. Again, you know that when you're exercising, okay, you take in more oxygen because you're producing more energy, but you're also producing heat. And we need to get rid of this excess heat. So increased physical or metabolic activity generates more heat in the body. For the body temperature to remain constant, this heat, extra heat, must be lost to the environment. So the body controls heat gains and heat losses, must control these in order to maintain homeostasis. Heat gain and loss is coordinated by a heat gain center and a heat loss center, both of which are found in the hypothalamus. All right, so what mechanisms do we have for increasing heat loss? As we generate this excess heat, one thing that happens is we will inhibit the vasomotor center. This will cause peripheral vasodilation. Okay, vasomotor. Vaso for vessel, okay? If you stimulate the vasomotor center, it stimulates the muscle in the vessel to contract and the diameter gets smaller. All right, so what happens here is we inhibit that center, and that will cause the peripheral blood vessels in our periphery, in our skin, to dilate. Warm blood from our core will be shunted to the surface of the body, and our skin temperature rises, and this heat can be dissipated into the environment. We also, as we start to increase or create this extra heat, the sweat glands will be stimulated to increase their output, and we perspire. This perspiration will flow over the surface of the body, and then as it evaporates, this causes an increase in heat loss. This is why it is so difficult on a hot, humid day in the summer for our bodies to cool down. When it's humid, the air is already saturated with moisture. Our bodies are warm, we perspire, but there is no place for that perspiration to go. It doesn't evaporate off of our skin, and this is what makes us feel so hot, sticky, and uncomfortable. Thirdly, our respiratory centers will be stimulated. We will increase the depth of our respiration so that we exhale more heat. Think about a dog when they are hot, they pant. Now we don't pant, but our the depth, how deeply we breathe, will increase in an attempt to get rid of some of this excess heat. How do we conserve heat? The sympathetic vasomotor center will decrease blood flow to the dermis. It will cause blood vessels at the surface of our skin to constrict and shunt that blood into the core. So this will reduce heat loss to the environment. In cold conditions, blood returning from the limbs will be shunted to the deeper insulated veins of our core, and even to our deeper insulated veins within, say, our limbs themselves. This is known as a countercurrent exchange, exchanging fluids moving in opposite directions. We're taking fluid from the surface and shunting them into deeper veins. So it helps to trap this heat in the core. We can survive without an extremity in extreme cold, but we cannot survive without our vital organs. So it's a must to keep our core warm or at homeostatic temperatures all the time. We have two main mechanisms for generating heat also when our body is cold. One is shivering. Shivering, when we shiver, it's an increase in muscle tone, and so the muscles are contracting, and as they do, they are using more energy, and this produces heat. Shivering can increase our body's heat production by upwards of 40%. There are also some non-shivering mechanisms, and this is done through the release of hormones that will increase our metabolic activity, especially thyroid hormone. This can also raise our heat production in adults anywhere between 10 and 15% over an extended period of time. Hormones also have an effect on thermogenesis. TSH, thyroid stimulating hormone. This stimulates will stimulate the thyroid hormone, causing an increase in thyroxine production. And remember, thyroxine increases our metabolic rate. If your metabolic rate increases, so too will the amount of heat. So thyroxine will increase or raise the rate of carbohydrate metabolism. This raises the rate of catabolism of all of our other nutrients in our body as well. And again, the more catabolism, the more metabolism we're carrying on, the more heat we will produce. Epinephrine will also can also increase heat. Glycogenolysis in the liver and skeletal muscles will increase as a result of epinephrine. And epinephrine also has an effect of increasing the metabolic rate of most tissues in the body. Now, there is thermoregulatory variation in all adults. Normal responses vary according to body weight and the distribution of weight in the body, as well as the relative weights of the different tissue types. Look at adipose tissue versus muscle tissue. Muscle tissue has a higher metabolic demand than adipose tissue. So you can have two people that weigh exactly the same, but the person who has a greater percentage of muscle mass will have a higher metabolic rate and will burn more calories doing nothing compared to somebody that has a higher percentage of adipose tissue. This is why most weight loss programs try to build muscle mass. The more muscle you have, the more calories you are going to burn, even at rest. Natural cycles can play a role. Daily changes, our heat production tends to fall at night. Menstruation in women can have an effect on your metabolic rate, as too can a fever. There's an old saying that says, starve a cold, but feed a fever. There is some logic to this. When we run a fever, our body temperature is higher than normal, and we burn more calories to maintain that higher set point in our body. So if we're burning more calories, we need more nutrients to burn, hence feed a fever.